Um, Hello. Last class, um, we introduced a bunch of interesting, useful geometrical concepts that will be used in the context of uh, curves and dynamics on statistical manifolds. So let me give you a quick overview of what we accomplished in last class and proceed to expand it further. Very good. So here we go. So we have a simplex, a statistical manifold. This statistical manifold is going to be curved, and we're going to use coordinates. So it's a curved object. And what we would like to do is study curves on it. So this is the statistical manifold. Let us call it S. We're going to study curves. And the reason we want to study curves is that eventually we're going to want to study dynamics, how things move, how probabilities evolve. At any point, we would like to study velocities, and those are typically described by vectors. So, um, very good. If we consider all possible vectors at one particular point, we're going to generate the tangent space at that particular point theta. So the tangent space at the point theta, so if this is the point, this corresponds to the point of tangency there, you have a vector there, and of course for any other curve you're going to have different vectors. Um, Similarly, at the point theta, we can, well, just like we have curves, we may want to study uh, so here's the space of thetas again, the statistical manifold. Just like we study curves, we may want to study functions. So how do we represent a function? A function f is going to be represented by the contours of constant f. So this is what represents a function f. At any point theta, we would like to represent the gradients of theta, and this is exactly the representation that we may want to use for gradients. Well, just like a velocity is something that is assigned at a point, we would like to talk about the gradient of f at the point theta. And the way this is represented is precisely by giving the contour lines. So this is also a flat space. If this is the point of tangency there, we're going to represent a gradient by parallel lines. Basically, in the case of a vector, you represent the vector by giving a directed segment, and the strength or magnitude of the vector is the length. Here we also are giving a directed set of segments. It specifies a direction, and the separation between these lines is what's going to give us the magnitude of the gradient. And so these guys here are members, gradients are members of the cotangent space at theta. Very good. A vector is generally expressed in terms of, well, a tangent vector is going to be expressed as having components that are the derivatives of the curve theta as a function of lambda. And there are basis vectors that we may write in this schematic way, or we can write this as the I components, and these are the corresponding basis vectors. Gradients can be written in basically the same way. The gradient of f is going to be given by its components, and the basis gradients are going to be the gradients of the coordinates. Um, very good. There is then we can start before we proceed. Yes, there is a technicality here that becomes important. So the following technical point is crucial. A technical uh, point. When we say partial derivative of f with respect to theta, what we mean is you change theta I while keeping all the other thetas fixed. So we don't need to write all of this, but the idea is that this implies that the theta j with j different from I are fixed. In other words, you change theta I, keep everybody else fixed. Now, this actually is in conflict. This is in conflict with normalization. Since all the thetas here are supposed to add up to 1, you cannot change one of them while keeping all the others fixed. If you change one, you have to readjust all the others. And so what do we mean by this partial derivative here? That's the question. Well, what we mean really is we're going to be trying to move on the subspace that is specified by this constraint. Okay, so when we do that, then we can invent a the tangent bundle. The tangent bundle is going to be the set of all the composed of the basic. Let me put it like this. You have the basic S, and you have all the tangent spaces associated to S. So this is what corresponds to the tangent bundle. We also have the cotangent bundle. T star S, and it is actually, so this is this guy here, and we can do exactly the same thing here with the cotangent spaces. Here we have vectors. Here we're going to have covectors. This is this guy here. But now, because of the problem with the partial derivatives, we have to be very careful about what we mean by these guys. So the way to fix the problem with normalization is we consider dd thetas as being, in order to define these properties, as being unrestricted. The theta i's to be unrestricted, which means that there is no normalization here, and so the simplex n plus 1 is embedded in the full space of dimension n. So basically, instead of having, in the case of the two simplex, instead of having 2, 3, instead of dealing with the simplex S2, we're going to deal with the full three-dimensional space, and we're going to write this as Sn minus 1. Actually, this is not quite correct. We should write it as embedded in a space. We're going to take the two-dimensional space and embed it in a space of dimension n. Okay, so this is dimension n. It is not a simplex. Nothing is normalized in this space here. And we're going to just write it as a space of dimension one higher. So this is how we are going to handle the problem of probabilities are normalized. Now, this is it's sort of like a little minor technicality that we have to play with. These normalization conditions are constraints that we have to accept if we're dealing with probability theory. But I have to admit that it is a technical point, but this is eventually what's going to lead us to the fact that when you represent states in quantum mechanics, you're not going to be representing the states as vectors in a Hilbert space. You're going to be representing the states as rays in a Hilbert space. You're always allowed to change the size of a Hilbert space vector without it reflecting a different state. So it's going to be an important part of the formalism of quantum mechanics that you have this constraint to play with. The solution is going to be just embed in a larger space. Now, you might ask, but wait, couldn't we just say we take the first n minus 1 coordinates and deal with those? Theta n is a function of the previous one, so there are only n minus 1 parameters. In principle, you could do that. But to deal with quantum mechanics, we really are going to have to deal with spaces of infinite dimension. And so when you're dealing with spaces of infinite dimension, it's very difficult to single one of these axes, single out one of these axes and call it the special one that's dependent on all the others. When you have infinity, you just can't do that. So it's just much better to just bite the bullet. You're going to have n coordinates, of which only n minus 1 are independent. So you have a constraint. We have to deal with constraints. We deal with unrestricted probabilities and in a space that is larger. So what we really are going to have is we're going to have a space ts plus 1, and when we consider all its tangent spaces, we're going to have the space ts plus 1, the tangent bundle. And most importantly, we're going to deal also with the space of covectors, not just vectors, but the space of covectors. So if this is ts plus 1, we're going to have ts star s plus 1, which is the cotangent bundle. So let me draw you another picture. I'm just writing the same thing over and over and over again so that you sort of like become familiar with the figures, with the geometry. You have a base manifold, which is one more dimension than the simplex. At any point theta, I'm going to draw it up here. We're going to draw the tangent space at theta. And here, this is going to be the space of vectors, all the vectors. Now at the same point theta, we can draw another flat space, which is the space of covectors. We call that Ts, oh, this is Ts plus 1. Ts plus 1 theta. Very good. Now we are ready to do something interesting. This is going to be our important object. Let me see what we do next. Yes, in this space, let's go back. Just like we had invented vectors on S, and we had invented covectors on S, we can now invent vectors and covectors on this larger space. Ts plus 1. And the idea is that we have points. This is a curve. The points are going to have coordinates theta and pi. Theta are the coordinates on the base space S plus 1. Pi are the coordinates of possible covectors on the tangent, on each tangent space. So you can fix a point in this space. Let me see now. Here I forgot. Let me see. This is the space of interest, the cotangent bundle. Very good. The vectors then on this space are going to be derivatives of these coordinates with respect to lambda, and we're going to write them like the theta I plus the pi I, the lambda, the pi I. And we're going to represent this in a nicer notation by saying if your curve is described by a parameter lambda, then these guys here, well, it's just lambda and pi lambda. We can write this guy as being x with this composite index that we discussed last time. Well, it's not responding. There we go. Alpha I d x I, where alpha equals 1 refers to theta and alpha equals 2 refers to pi. So this is theta, alpha equals 2 refers to pi. In the same way, and because now everything is unrestricted, right? We increase the dimensionality of this guy we increase the dimensionality of S by 1, and therefore they increase the dimensionality of the cotangent bundle also by 1, right? You increase 1 here, you increase 1 there. Then the gradient is perfectly well defined now. The gradient of any function, we can write it just as the derivative of this f with respect to these coordinates, and here multiplied by the gradient of those coordinates. I think we're good. Okay, with this, it takes us to where we start doing something new right now. So vectors and covectors. Okay, so here we have vectors, and there we have covectors. Very good. These are the objects that are going to be of interest to us. And we have to always remember that really we're talking about this is the object that would also be reflected, expressed as the I, and then here the theta I, and then the F, the pi, and gradient pi. Very good. Now we're going to start talking about structures that we can impose on this space. Um, One of the things that happens when you have at each point, when you have a tangent space of vectors and a cotangent space of covectors, is that you can find maps that take you from vectors to covectors and back. And that's going to be useful. So we want to introduce the symplectic form. So let me start talking about this, motivate what's actually going on here by changing the subject. Uh, if you can have a metric structure. Uh, Let me write this as the symplectic structure. What is this? Well, uh, a metric structure, sometimes you have additional conditions on your manifold, and you may have a metric structure. A metric structure, this is just saying you have a metric tensor on the manifold, makes it rigid. Once you have a metric on a manifold, you cannot just go ahead and start stretching it in any way you want, right? The distances between points are going to be sort of fixed. So this is telling you something additional to what you might have known about the manifold. And so the way we tackle something like this is we say, look, if you have a metric tensor is something that comes with two slots, and if you put two slots there, so this is a linear machine that if you have two arguments, it gives you some scalar. The scalar, of course, is G I J B I and A I B J. Something like that gives you a scalar. Very good. If you were to leave one of the two slots open, what is this? Well, basically recall the following. If you have a covector acting on a vector, this gives you a scalar. In this case, the scalar is something like an expression of this form, right? So when we have something like this, an object like this, what we have is something that if you were to put here a vector, you would get a scalar. So the conclusion is that whatever this object is, this is a covector. The components of this covector, what are the components? Well, just like we had here, the components of these guys, you can see are going to involve Gij, AI, and then something to be inserted in that slot. something like that. So this is going, notice that here, the object that we have uh, has the index I is being summed over. So it, whatever it is, it has the, it's a quantity, let's write it like this, that has an index j downstairs. In fact, what this is, whatever this monstrosity here might be, uh, this is the covector associated to the vector A by the metric tensor. And so by definition, we're going to call this as the covector index downstairs associated to A. And so this is the notation that we use for this particular map, something that takes you from the tangent space of vectors to the cotangent space of covectors. This is called raising the indices, or rather lowering the index. You take a vector with an index I upstairs and you apply this and you transform it into an index j downstairs. Very good. Why am I doing all of this? If you impose a structure, you make the manifold more rigid. You give it structure. That's what structure means. The particular structure imposed by a metric tensor is one that maps vectors to covectors, and the inverse, that's the opposite. And it's something that behaves in this way. So this is just motivation. Where I'm going with all of this is that there is another kind of natural object that we can invent associated to the manifold that also provides structure. So here the symplectic structure. And the idea is the following. Given coordinates theta and pi, given local coordinates, just given coordinates on on the cotangent bundle, and the coordinates are theta and pi, we can invent a very natural anti-symmetric tensor. This is what the anti-symmetric tensor is. We're going to call it omega, and it's an object that has room to act on two vectors. So we're going to put here vectors. Let's call them V and U. That's what they're going to act on. And this is what the object looks like. Uh, it's supposed to, when you act with this here, it's supposed to give you a scalar. So far, this is very similar to the metric tensor. The one big difference is that the metric tensor is symmetric when you exchange V and U. This guy here is anti-symmetric. Otherwise, it's very similar. We say that the metric tensor gives a metric geometry for the manifold. We're going to say that this guy here, which is called the symplectic form, gives it a symplectic geometry. So we have to develop some intuition about what this means, but what is the form of this tensor? Well, the form is that it's going to have two slots, and it's going to produce a scalar. What are the objects that have slots open so that when you act on vectors, you get scalars? Those are the covectors. So let us put here the covector theta, which can act on one vector, uh, tensor product with the covector, the gradient of the coordinate pi, which can act on another. So now you see what I have here. What is this? Is an object. If I supply it with two vectors, vu, v, and u here, putting v here is going to give me a number. Putting u there is going to give me a number. Whatever this is a scalar, so I'm satisfying all of that. But now I'm going to make it anti-symmetric. We're going to have now that in the opposite direction, change the sign and put them in the opposite direction. So this is what the anti-symmetric tensor does. In particular, okay, how natural is this object? How Please notice I didn't have to do much. Once I said, once you have coordinates, you can always do that. Once you have these coordinates theta pi, you can always invent something like this. Okay? So this is something relatively natural to consider. And so notice now that if I were to have this omega, and it comes with two slots, and I put a vector here, say v, the object that we now have is an object that accepts a vector to produce a scalar. So in other words, this object here is a covector on the space that we're talking about, the cotangent bundle. So now we have two ways to map vectors to covectors. One way is the metric tensor. That's the process of raising indices. This is a different way, and it has no name, but we'll continue and see where this leads us. Yes, we need a couple of little formulas here. The way that this guy, how do we act with omega on a vector v? Well, we put the v here and there in the first slot, right? V in the first slot corresponds to v in the first slot. So we're going to use the following. The gradient of theta I acting on v. Remember that this functional here, the gradient, is linear. It's a linear operator, so this is going to be v. Well, let's just go through this slowly. Gradient of theta I, and then here we have v, which is the vector v is going to be, we want to write it as alpha I, and then of course the vector, the basis vector alpha I, and when this being linear, we want to pull this v alpha I out, and then we have the action of this. Here we should have a different label here, j, and this is theta I acting on the vector alpha j. Now, the way we want to do this is that this vector acting on, when this alpha here is 1, this guy gives you a Kronecker delta. When this guy here is 2, it gives you 0. So this guy is just going to be V1I. So that's what the acting on a vector is going to give you. Similarly, this guy gives you the component as well by I. Acting on the vector V is going to give you the second component I. So now if we substitute these guys here, what we have is that omega acting on V with one slot open for introducing another vector is going to be, where are we here? V1I gradient pi I minus V2I gradient theta I. So you can see that this is indeed a covector, has room for, this is where you would put the second vector, the argument, the window for the second argument. And if we have two vectors, the action of omega on two vectors is going to be immediately V1 I U 2 I, where you sum over I, and then minus V2I and U1I. So there you have the action of the vector on two of omega of the symplectic form on two vectors. You can see that it is anti-symmetric. Very good. We would like to know what are the components of this vector, the components of this tensor. The components, we're going to write them as alpha I, beta j. And it's easy to see that these guys are just going to be this acting on alpha I, e beta j. And the way this actually works is that if you have VU, this is going to be alpha I beta j V alpha I U beta j. We're just adding. You see, you just have more indices, but this is in no way different from doing something like we had up here when we just were dealing with a genetic manifold. You just sum over the various components of the metric tensor acting on vectors. Same thing here, no difference. Except that now, because this guy is one of those, and that guy is one of those, and the differences, so here we see we have, what we have here is components with minus signs with a 1. And here we have components with numbers. This tells us that whatever these numbers are going to be either 1 or minus 1, or you don't have a 1, 1 or a 2, 2. So 1, 1 does not appear here. 2, 2 does not appear here. Whatever this object is, as far as the alpha and beta indices go, it's going to be something like that. So this is the alpha 1, 1, alpha beta 1, 2, 1, 2, That's the 1. 2, 1 is the minus 1. 2, 2 is there. And as far as the ij goes, it's just I. Very good. I think it's time to stop here. Uh, Before we proceed, let us recollect our thoughts and see what it is that we have done here. I said, look, if you have a metric structure, then you have this tensor that allows you to produce scalars. But if you leave one of the slots open, then this object very much behaves as a covector. In fact, the covector that you have here is something that takes a vector, right? This map is this whole object is a covector. It's like taking one vector A and from it producing a covector that we define with the same letter A and with lowered indices. We do exactly the same thing in the case of the symplectic structure. Once you have coordinates theta pi, we invent this anti-symmetric tensor, which is purely built from the uh, gradient basis, right? Comment. It's very interesting that here we are getting we have twice the dimension, right? If this is dimension n, this is dimension 2n. So now we're really dealing with this in this space of dimension 2n, and we have doubled the number of coordinates from theta to theta and pi. When you actually apply this tensor that we have invented here to vectors, well, just do it. You operate with them in the normal way, compute what the action of these gradients are on vectors, you get the components, and the tensor that we have obtained here is very, very simple. It has this, it's diagonal, actually it's diagonal when it, when it comes to the ij indices, but it is anti-symmetric and off-diagonal when it comes to the indices that relate theta and pi. In the next section, what we're going to see is why this tensor is really important. See you then.